All right, last time we started section 6.1, talking about rational numbers, and I believe we had left off on taking a look at the different models, and these were those. There is one caveat to the set model that I failed to mention that I think is probably worth mentioning anyway. So if you're using the set model where you're given the objects to start with and the objects match the denominator or they're easy to sort of separate and figure out from the denominator, it works really well, right? So if it's 3/4 and I've given 4 objects, I shade 3 of them in. But that's not very helpful if you're given, say, 5 objects and you need to know what 3/4 of 5 objects are. So there is some sort of a limiting behavior to the set model that the other models don't quite have. So I just wanted to mention that because it's not as user-friendly. All right, so we're going to start with, for today, Theorem 6.1. This is called the fundamental law of fractions. So if you have a fraction a over b and n is any non-zero integer, if you multiply by the top and the bottom of the fraction by that value n, the fraction's value doesn't change. So it's another fraction of equal value as the one you started with. So it's an over bn. Sometimes we use it in that fashion in order to find like common denominators, which we'll be doing later today. Sometimes we use it sort of in the backwards of that fashion to simplify fractions. So simplest form, a rational number a over b is in simplest form if, first of all, the denominator is positive. So we want the denominator to be positive. The numerator could be negative, but the denominator is positive. And the greatest common divisor of a and b is 1. So it just means that the top and the bottom don't have any common factors. I can't reduce them by dividing them both by the same value. All right, so the first example that we're actually going to do today, example number 2, is to write fractions equal to 7 over negative 14. So using the simplest form idea or the fundamental law of fractions, we can actually create lots of fractions equal to this one. So the simplest thing we can do, that you might not always think to do, is that we could actually multiply or divide, depending on your perspective, the numerator and the denominator by a negative. In other words, we can actually find negative 7 over 14. Super not very interesting, but that's an equivalent fraction. If you're thinking about it from a simplifying perspective, we could also simplify by dividing the top and the bottom by the same quantity, right? So we could divide both, for instance, by 7 and turn it into its simplest form, at least ignoring the negative part of it, to have 1 over negative 2, or you could write it as negative 1 over 2, or you could write the negative in front of the whole thing. That'd be another version of this that would be equal. You could also even just start with the 7 over negative 14 that you have, and you could multiply by something on top and bottom. So maybe you decide, I'm going to multiply by 3. Arbitrary, but why not? So I get 21 over negative, I think that's 51 on bottom. Is that true? 17? It's 14. I might have been thinking about 17. That's not working for me. 42. I was thinking about 17, not 14. There we go. That makes more sense. And of course, that answers the question. I found 3 of them, right? Actually, I found 4 of them. But there's infinitely many others that you could put that would be just as good. There's absolutely nothing better about my 3 than maybe what other things you come up with. And in fact, they're not even the same 3 that are in my notes from when I did the last one I did it. Okay? So lots and lots of options when you're asked to write equivalent fractions. Now, in the next one, if you're asked to find the simplest form, there really is going to be just one answer. There is a simplest form. I bring this particular one up because there is sometimes this misconception that we have based on simplest form over here, that we're able to cancel things from the numerator and the denominator in ways that maybe we actually aren't. So the numerator and the denominator here on this fundamental law has the ability to sort of think about the fact that you could cancel the n out if it were given in that form, right? And you can, and that's true, but that's because those are both being multiplied. On this one, sometimes I have students want to be able to cancel out squareds. But you can't, because squaring is not the same operation as multiplying the same value on the top and the bottom. So that's not a legal operation. What you can do, however, is you can take the 42 and you can write down 42 times 42, and the 35 and write down 35 times 35, and write it in a multiplication form. And then you can look for common factors. For example, hopefully, if you're thinking about multiplication tables, you do recognize that 42 and 35 do have something in common. What are they both divisible by? 7. And I can divide the 7 out of both pairs. So I can divide the 7 out of one pair, which leaves me with a 6 here and a 5 here. And I can do it over here too, leaving me with a 6 and a 5 for that pair. So now I have 6 squared, which is 36, over 5 squared, which is 25. I actually know that there's no way I can simplify that, and the reason I can't is because 5 is prime, and 5 doesn't divide 6, right? Can't break 6 down and have any 5s as factors. So even though these are kind of larger numbers than maybe the last problem we did in simplest form, this is the simplest form for this particular fraction. Okay, everybody good on that? Okay, so no canceling squareds. Theorem 6.2 talks about another way to determine, we're going to talk about several ways to determine if fractions are equal, and this is one of them. One you're probably familiar with. So if you have fractions a over b and c over d, then those are equivalent if AD is equal to BC. And what people usually recognize is that you're able to take these diagonals and multiply across your diagonals, and if you have the same value when you multiply across your diagonals, then the fractions were equal, right? There's lots of cases where this works really well. If you're just wanting to know if it's equal, that's great. It doesn't help you in the way this actually is set up at the moment to deciding which one's bigger or smaller. You have a little bit of a difference to this particular theorem if you want to do that. But there are other ways to determine if fractions are equal too. So we're going to take a couple of fractions and we're going to look at 4 distinctly different, although related of course, ways to decide if fractions are equal. So as we sort of move into this idea of me showing you multiple ways to do something, here's what I want you to know. So on a test environment, if I don't tell you, or if your book and you're doing your homework doesn't tell you how to show this, you get to pick what you want to do, right? But you need to know all the ways of doing it, because if your book or if I on a test ask you to do it a specific way, then I'm going to be grading for do you know that specific method. So it could go either way in a direction set. But I want you to see 4 different ways of doing this. And the reason I do is not because I'm trying to be a pain in the rear. I mean, like, I'm really not. It's because your kids in your classroom someday, if you're asking them to do something like this or anything else, and you specifically tell them one way to do it, and it's not making any sense, that's probably not the time to be like, you have to do it my way, and I don't care if it doesn't make any sense, right? Probably a better idea to find another way that does make sense to them so that they can move forward with their building of mathematical knowledge. So I want to give you lots of options of things to think about as I come across them so that you have that ability to pass on to your students. So the first one we're going to do is with the theorem, because we just talked about it. So the first option is Theorem 6.2. So we're going to decide if these are equal. So this is 3 over negative 12. And I'm going to put the equal sign between them with sort of a question mark on top of it. We're trying to decide if it's equal to 36 over 144. I'd kind of like, actually, to ignore the negative. They're both negative. So that's not the point, right? They both have that in common. So as I look about whether or not these are going to be equal, I actually can sort of ignore the negative part of it because they are both negative values, and just consider the fractions themselves without the sign. So Theorem 6.2 says I can multiply across my diagonals to see what I have. So we'll start with the 3 times 144 first. What is 3 times 144? Grab a calculator if you don't have one out. 432 is right. So that's the red diagonal I just did. And then what is 12 times 36? It's also 432. So when I cross multiply, I do in fact get the same quantity. So Theorem 6.2 says that they are in fact equal. So these check out, which means that the fractions are equal. So if you were not given any instructions on how you wanted to or were supposed to solve this problem and you did it this way, you would be done. Okay? One thing to be aware of is that those numbers are kind of big. You probably grabbed your calculator and didn't actually multiply it out by hand. That's sort of a little bit of a drawback, especially if you're working with young kids who aren't going to be using their calculator. They're going to actually have to multiply it out by hand. They might not prefer this because these numbers are a little larger than maybe what they wish they were. All right, so let's do a second way. The second one is maybe the most helpful in terms of making things smaller. So the second way I'm going to show you is to simplify and compare. So we're going to start with the 3 over 12. And we're going to ask ourselves to reduce it to simplest form. So what do 3 and 12 both divide by? Yeah, they both divide by 3. So 3 divided by 3 is 1, and 12 divided by 3 is 4. And we're going to do the same thing to the other value. So I have 36 over 144. Now, depending on what you remember about multiplication tables, you may decide, hey, they're even, I'm just going to divide by 2. You may look at that and say, hey, I recognize that those are both divisible by 12. And you might do 12s. You might say, hey, they both look like they're divisible by 4 and go with 4s. There's lots of things you could divide by. The point is that you don't stop dividing until you're actually finished. So perhaps your kids recognize that this is divisible by 12 because they've learned their multiplication 12 tables. That's definitely possible. If it's not and they start with something smaller, that's fine. What is 36 divided by 12? Yeah, it's 3. And then 144 divided by 12 is another 12. Now 3 over 12 should look familiar. That's what the other one started out as. But let's say, for instance, it wasn't 3 over 12, it was something else. Well, we would keep going. We would divide them both again until we get to simplest form. And of course, in the end on this one, we do get the same 1/4. So again, since these two are equal, then it means the original fractions are equal too. If, when we reduced them, we got down to something like 1/4 and 1/3, right? Then we don't need to, I mean, they're obviously not equal. They're both in simplest form. They're not the same. So simplify and compare. Let's do number 3. The other two have to do with common denominator approaches. So number 3, we're simply going to find a common denominator. And then number 4, we'll find the least common denominator. Okay? So for right now, just any common denominator. Sometimes it's hard when you look at numbers to see what the least common denominator is, especially if students are not real good with their multiplication tables or recognizing factoring. So it's always possible when you're looking at two values to find a common denominator. So we had our 3 over 12, and we have our 36 over 144. So you find common denominators in general simply by multiplying the two denominators by one another. Okay, so the what do I do is the next step is very straightforward on this one. So I would multiply this denominator by 144 and its numerator. And I would multiply this one by 12 and its numerator. Okay, so you're just multiplying by the opposite denominator, whatever it is. That creates large numbers. It's kind of a drawback. If you are utilizing a calculator, it's not a very big drawback. 3 times 144, we did that before and found 432. What is 12 times 144?
1,728.
Good. 1,728. Now that's going to match the second one because it's the same 144 and 12 that we had down there. So the denominators matching means that if they're going to be the same, the numerators would have to match as well. And then 36 times 12, again, we did that before. We found it was 432. So these two are equal. Right? So my original fractions are equal. Okay, so I'm trying to get any common denominator, compare the numerators. 4 is nicer because it keeps things a little smaller. So 3 is nice because you can just start it no matter where you are. You don't have to think about factoring or breaking anything down. But on this one, oops, let me label it. So we're going to find an LCD, least common denominator. 3 over 12, 36 over 144. You're looking at how you can change one denominator either into something or find a common factor that they have, or a common multiple that they have in common. 12 and 144 are very nice because 144 is a multiple of 12. In other words, I can multiply the 12 by 12, and now my denominator here, 144, will be the same as the denominator there. It doesn't always happen that way. Sometimes there's more breaking things down to that. This, of course, gives me 36 over 144, just like I already had on the other fraction, right? These are equal. So the original two fractions were also equal. Okay, so that's just being able to compare, are they equal? There's a very slight change, and we can actually compare which one's larger using that same Theorem 6.2's idea. And that is happening in Theorem 6.3. So Theorem 6.3 actually tells you how you would determine which one's larger if they're not equal. Okay? So you see the same cross multiplication happening, right? So here's that A times D. Here's that B times C. And it's telling you that if the yellow diagonal is larger when it multiplies, right, the A times D, than the red diagonal was, then the original fraction on the left was bigger than the fraction on the right. So everything stays in the same order as long as you start in the top left-hand corner, which kind of makes sense to us because that's how we read. We read from top to bottom, left to right. So that's sort of a beckoning that makes sense to us. Now, the thing that's tricky is that doesn't allow us directly to answer question number 5 because it compares 3 numbers and not just 2 numbers. So I'm going to pause on example 5 and go to example 6 because I think that it's a better example of the comparison piece. And then we'll jump back over to 5 and talk about, well, what happens if there's multiple numbers? So if we want to use that theorem, we can on number 6. There's another way to do number 6 as well, which we'll come back to a couple of them. But let's do theorem, it was 6.3, right? Yeah, theorem 6.3's approach to number 6, just so that we can talk about how that plays out. So I have 21 over 430, and I have 51 over 215. And I'm going to put just a question mark in between them because I don't know. Is it larger than? Is it greater, equal to? Is it smaller than? I don't have an idea of where to start. So we're going to cross multiply along our diagonals. So one diagonal, always start with the top left, 21 times 215. The other diagonal from the bottom up is 430 times 51. So grab your calculator if you'd like. What is 21 times 215? 4,515, thank you. And what about the other one, 430 times 51?
21,930.
Fabulous. Very clearly, 21,000 is bigger. So if you think about sort of moving up, the equality statements here, this one's bigger, which means this one's bigger, which means the original one was as well. The same sign goes straight up. So what we know is that 21 over 430 is less than 51 over 215. And that's one approach to proving that or verifying that. Let's look at 2 other approaches on this one, and then we'll jump back into to problem 5. These 2 other approaches are going to look a lot like what we did when we found out if the fractions were equal. So one of them is reducing or simplifying, okay? So we can take the 21 over the 430, and we can take the 51. Let me, instead of just saying reduce, let me say or get things in common, because it depends on the fractions as to which approach might be helpful. 21 and 430. 21 is only divisible by 3 and 7. Agreed? 430 is not divisible by 3 or 7. So these are actually in reduced form, at least the one on the left-hand side is, because 21 and 430 have nothing in common. The 51 and the 215, so 51 is divisible by 3. And so I think they're both divisible by 3. So one option is we can divide these both by 3. Okay, because they do both have that in common. If I do that, I don't have this one written down from this perspective, so let's just run it through it together. I have 17. Oops. 215 is not divisible by 3. Sorry, 5, 6, 7, 8, 9. Yeah, it's not divisible by 3. I take it back. That's probably why I don't have it written down that way. Okay, so 51 is divisible by 3 and 17. Unless 215 is divisible by 17, which I doubt, then they are in reduced form as well. Yeah, it's not. Okay, so these are in reduced form already, which doesn't help. But the denominators have something very nice in relationship to one another. What's that?
215.
You got it. The relationship that exists is that one of the denominators is double the other one. So we could get a common denominator as a way to compare, since reducing is not an option. So we still have that same 21 over 430. And now I've got a 430 in the second denominator. And what's my numerator going to be? 102. And 102 is most assuredly larger than 21. So once again, the direction of the inequality opens towards the 102, which is larger, which again means my 51 over 215 is larger. Okay? There's one other really cool thing, and again, it kind of just depends on the numbers you're given. But some of you might have looked at this and said, why are we even trying? Obviously, the second one's bigger. So if you're of that mindset, what you might have noticed, or if you're not, what you might notice now, is that if we estimate or think about this from a reasoning standpoint, we reason through what we have, the second fraction is most definitely bigger. And the reason it's bigger is because the denominator is smaller, so you're dividing it into fewer pieces, and the numerator is automatically larger. So when I talked about estimation, I think that that's a good approach. That 51 over that 215, for example, it's almost like you have 50 over 200, right? Like that's not exactly the same, but that's pretty close. If you were trying to do a real estimation, like a real calculation with this, 50 over 200 would be much nicer than 51 over 215. And this, when you divide both top and bottom by 50, is 1/4. So the 51 over 215 is about 1/4. But if we try the same sort of, approximation strategies with the 21 over the 430, you might change it to something like 20 over 400. That should say approximately. Sorry, let me get the eraser. Seriously. There we go. So 20 over 400, by both divide by 20. So there's a 1 on top. And what's 400 divided by 20? It's 20. Yeah. 1/20th is much smaller than 1/4. Now, if the numbers are a little closer together, this is not necessarily a great approach, right? But on this one, it's pretty reasonable because they're so significantly different in value. So again, 1/4 is much larger than 1/20th, making the 51 over 215 larger than the 21 over 430. Okay, so 3 different approaches. Again, sometimes you're asked to do it a specific way, oftentimes you're not. So let me show you what happens then if you have 3 values. So with 3 values, you can compare them like 2 at a time. That might be useful because you might find, a nice ordering. But you also might say, hey, I'm going to compare 13 over 20 to 3/5, and I'm going to compare 13 over 20 to 7/2 or 7/10, and you find they're both bigger than the 13 over 20, and you're like, okay, well, now I got to compare something else again. So you have to make yet another comparison. So you might end up having to make 3 comparisons instead of just making 2 comparisons, depending on how things work out. So instead, this option that we had on the second one where we were looking for reducing or finding common denominators is often a very nice approach because instead, if we get all the denominators to match, which is a nice approach to doing that, it's easy to compare the numerators. So take a look at the denominators given on this one, 20, 5, and 10. What is a nice common denominator that I could shoot for among those three? 20. So one of them is already 20, so that's friendly. I can turn 5 into 20 by multiplying by 4. And I can turn the 10 into 20 by multiplying by 2. So if I do that, I have 13 over 20, 12 over 20, and 14 over 20. It says ascending order. So ascending means smallest to largest, like you ascend the stairs. So which one's the smallest? Yeah, the middle one in the middle, which is the 3/5. You could put a comma, or if you want to give the structure with the inequality notation, you could put less than. Which one's the next largest? The 13 over 20, which was the form it was given in. And then the largest one is the 14 over 20, which is really 7 over 10. So we want the answer to match the problems that we were given, like the actual values that was originally given, but we're changing them into common denominators to make them easier to compare. Any questions on comparing order of fractions? All right, Theorem 6.4 talks about denseness. So the denseness property for rational numbers says that if you're given two rational numbers, there's always a number between them. Okay? So why is that? Well, because there's always space between the numbers on a number line, right? So Theorem 6.5 actually goes through and tells us how we can find such a number. And it's not the only way. Another option, which is sometimes what people choose to do, is to sort of add the two numbers together and divide by 2, right? We'll do something really easy. What's halfway between 3 and 5? Well, 3 plus 5 is 8. 8 divided by 2 is 4. So it's 4. It's halfway in between. And that works great for whole numbers. It doesn't work so great if you say what's halfway between 3/5 and 4/5. Well, now I have to add 3/5 and 4/5 together, and then I have to take a fraction and divide by 2, and it's kind of messy. And if the denominators are not the same, it's even messier because I need common denominators to add them. I mean, like, that's not an easy process. So the beautiful thing about Theorem 6.5 is it says instead of adding the two fractions together and dividing by 2, I actually can add the numerators together and the denominators together, which is really easy because it's usually whole number addition, right? 3 plus 4 is my example before. 5 plus 5 is 10. I mean, it's easy addition. And the resulting fraction will be between the two numbers I started with. So it's very, very handy. So when you take a look at this one, right, these numbers are not pretty numbers. 33 over 427, 7 over 92, no thank you. Those would be terrible to try to find a common denominator for and add them together and divide by 2. That would be awful. But it's really easy to find a number between them using Theorem 6.5 because we can take the numerators, 33 plus 7, and the denominators, 427 plus 92. We can add them together. And we still may have to reduce at the end. That's a possibility. But the addition part's very easy. The top's 40. I'll do the easy one. Somebody tell me what you get when you add those two denominators together. 519 is right, yes. Thinking about the number 40, it's divisible by 2 and 4 and 5. Yeah, 519 is not divisible by any of those. So I'm actually don't even have to do any reducing on this particular one. I could have, but I didn't. 40 over 519 is in between them. Now, while we're not talking about decimals right now, if you're looking at that and you're like, how do I know? You're welcome to put all three numbers into your calculator, turn them into decimals to kind of compare them and see them from a decimal perspective. Again, we'll talk more about decimals in Chapter 7, so we're not doing that right now, but you could do that if you wanted to as you're checking to your own work. So why must there be a number between these fractions? Well, the reason is because rational numbers are dense. that is you can always find a point halfway I don't think halfway is hyphenated. After I did it, I was like, that doesn't look right. You can always find a point halfway between two numbers. And it will be rational. The reason I mention halfway is not because it's special in the sense that it's the only one, but that it's special in the sense that it's easy to justify why it has to be a rational number. If you add two rational numbers together and divide by another rational number too, it's still a rational number. All right, so we're going to talk more about that property later. But that is a property of rational numbers, is that when you work within the rational numbers and do all these operations, it all stays rational. So halfway between, dividing by 2 is a rational number. So we are going to find another rational number. Okay, some of what we do in this class will be analyzing student work, because someday you're going to teach something and students are going to do some kind of work, and you're going to have to be able to identify some things that they do wrong so that you can help them fix their mistakes. So we're going to do that together on some examples throughout, both in class and in your homework. Here's an example of one of those. A student simplified the fraction m plus n over p plus n to m over p. So what did the student do?
Student canceled out the ends.
Yes, not just the n's, but like the plus n, right? So the student canceled the plus n parts, right? This is what they did. They said, hey, look, there's a plus n here, I can cancel them. Why might they believe this is a valid operation? Yeah, and we saw something where this is a valid operation when it's the same thing top and bottom, right? So it's the same, and I actually really like the way you even said that, kind of this arbitrary thing. It's the same thing on the top and bottom. There is a place, and we talked about it today, where this idea of canceling the same thing on the top and bottom works. Where was it?
It was Theorem 6.
Okay. So in Theorem 6.1, what did it say? What can we actually do? What is the thing that we're allowed to cancel?
When they're multiplied.
Multiplied. Yeah. So in Theorem 6.1, when n is multiplied, on the top bottom, it can cancel. So this is probably what they're thinking of, right? They're thinking of the idea of what multiplication does. They may not even realize that they're missing that it's a different operation, right? But this idea of being able to cancel something out on top and bottom is sort of ingrained in that, and they did it, and so they did it the same way. So aside from simply telling them that's a multiplication operation, this is addition, addition doesn't work that way, how could you actually show them that this isn't going to work? Yeah. So numerical values into something is often very helpful. And in fact, most of the time this won't work, so you're probably pretty flexible in picking something and finding something that doesn't work. For example, maybe you decide that you're going to use 1 and 2. You have to make sure that the 2 is the same because it's the n, right? And 3 and 2. Just pick those randomly. If I do this, I get 3 on top and I get 5 on bottom if I actually do the addition, right? But if I reduce it the way that they've suggested, I get a 1/3. So this is what their idea would leave me with. This is what it really should be. And how can I show that these are not equal? Or what can I do to talk about them not being equal? There were 4 ways we did it. You can find a common denominator and compare the tops, right? Or least common denominator. You could talk about the fact that they're already in reduced form. And in reduced form, they're not the same. Or you could cross multiply to show that when I multiply across top to bottom on each set, they don't equal the same value. But a numerical value is often very helpful for students because sometimes we can talk ourselves into anything, no matter what somebody else says. But if you see a concrete example where it fails, you're kind of stuck then, right? So concrete examples are often very helpful. All right, there's one more example in this section, and I'm going to run through it quickly just because it's interesting. It's an example from your book, and I don't even know if it's in the book still, to be honest, since they've changed editions, that comes in this section C problems, which we'll talk about in a little bit. It says if we take a set of numbers equivalent to 1/3 and graph them as points on an xy axis so that the numerator is the x coordinate and the denominator is the y coordinate, what type of graph do we get? So if I had more time, I'd let you delve into parsing out all the pieces of what it's saying. But I want to move through a little more quickly than that. It says we want a set of numbers equivalent to 1/3. So we want things like 1/3, 2/6. Whoops, yeah, that's right. We can do -1 over -3. And honestly, 3 points is enough. I mean, three equality is enough. There's 3 numbers. They're all equal to each other. And then what we do is we let the tops be all the x coordinates. That's what it's saying here. These are my x's. And the bottom are all the y's. So I have an ordered pair 1, 3. I have an ordered pair 2, 6. And I have an ordered pair -1, -3. So far, so good? And we're going to graph them on a number line. And yeah, I was like, I think I have a number line set up on the next slide. If you do, or not a number line, but a grid. If you don't have a grid, it's not a problem. I think I can actually make my grid even bigger and it'll be more helpful. It's medium already. Let's try that. Let's see if I can have a big enough screen here. Okay, so here's my ordered, or my axis. It's not super straight, so please forgive me on that. But we're going to plot those 3 points. The first one was 1, 3. So I go right 1 and up 3. That's 1, 3. I had 2, 6. So right 2 and up 6 would be here. And then I had -1, -3, which would be here. Can you tell what these points are forming as I graph it? Yeah, it's a line. These actually do form a line. Sorry, my tools sometimes are a little sensitive for me. So that's pretty good. These form a line. It's a line that has some characteristics. Can you tell me some characteristics that you usually think of when you think of lines? What's that? It's infinite, that's true. What else? It's not exponential. It's infinitely increasing, though, which might be what you were thinking about. It's definitely increasing forever. There's a slope to it. So I'm going to talk about this. I'm going to not talk about, but I'm going to mention the slope because the slope's the same everywhere, which is something that's very unique to a line. So this line has a slope. Can you tell me what the slope is? Yeah, this is a line with slope 3. Normally, slope and y-intercept identify features of a line that allow it to be unique. Visibly, the way I've drawn it, this has a y-intercept at the origin, right? So it goes through the origin, but excludes it. And I want to show you why. The ordered pair of the origin is 0, 0. Does 0, 0 fit into these equalities? It doesn't. So we originally set up to only use values that have the same fraction equivalence, and 0, 0 doesn't do that. So it's on the line, but it's not one of the ordered pairs that actually satisfies the condition. So it really is not included because 0 over 0 does not equal 1 over 3, which is what we started with. So it's an excluded number from the line. So it's kind of an interesting example of ratios. All right, so a 6.1 is assigned. I'm going to turn this off and we're going to talk about getting the test or getting your homework done at this point.